Alright, let's move on. So let's look at the real DRAM fabrication process. It's simple from the circuit schematic point of view if you want to draw a DRAM as we showed in the earlier slide. So this is a transistor and then you have a capacitor, right? 1T, 1C. But if you really implement this into silicon, then it's not as straightforward as in this circuit schematic. So here the trick is on this capacitor. You first should fabricate the transistor into the silicon. So that's why you have the transistor like this. So it's NMOS transistor, we also show here, right? So you have the transistor, and then this is the transistor, it's 1T. And then, for example, this side, if this side attached to the BL, so you build a contact there, and then you attach to the BL line. That is fine. That is what we have here. And then the other side connect to the capacitor. Okay, here you connect to the capacitor. But you see here the capacitor is like a U shape. We call it stacked capacitor. This is on top of the transistor. So here we have a U shape capacitor. Why is that? So here we build this U shape capacitor. So why is that? The reason is we need to increase the surface area of the plate capacitor. You know, for a plate capacitor, right, you have two metal plates, and the capacitance is proportional to the area of those two plates. The challenge here is that for a lateral dimension, it's very small for today's technology. If you look at the market from Samsung or Micron, the capacitors here, the lateral diameter is only 10 nanometer. So 10 nanometer is very small. In order for us to have a large capacitance, we have to make it U-shape. So still, you occupy 10 nanometer lateral space, but now the surface area is much larger than this 10 nanometer by 10 nanometer. Because here we can define this D, and then we can define the height. So we call it an aspect ratio. Is this height divided by the diameter. So this can be up to 100 in today's advanced process. So that means if here, if you look at this, is a cross-sectional image taken from the real chip under the microscope. This is not the latest technology, but here as an example, we are looking at 10 nanometer here, and then 1 micrometer high. Then your surface area will be much larger, even though you only occupy 10 nanometer by 10 nanometer lateral space. But the surface area, you have to consider this height. So why do you want to have large surface area? Because this surface area, let's say larger surface area, the capacitance will be larger. And why do we need this capacitance to be larger? If you recall, in the sense margin, we want to have large margin to detect the data. So we need the larger capacitance for the storage node, that is the DRAM capacitor, larger than the parasitic capacitance of the bit line. So here, this is the way to maintain the cell capacitance and then to maintain the sense margin. Because this sense margin needs to be larger than the noise in the circuit. You want to deterministically read out the data 1 and 0. So you need to have a large enough sense margin. So that's why we have to build this U-shaped stacked capacitor to the top of the transistor. Any questions? All right, let's talk about the DRAM's data retention problem. So the DRAM is called DRAM because of this unique feature in the DRAM's data retention. That is, DRAM's data will be gradually lost over time because of the leakage to the capacitor. As you know, the capacitor can temporarily hold some charges there, but if there's any leakage current, then the charge will leak out. Then the voltage you store there will decay over time. For example, if you store 1 in the capacitor, then if the charge decay over time, the voltage decay over time, then your 1 will gradually become 0. Then you lose your data basically. So this is not good. That means we have to refresh the data once in a while. So this is why the DRAM is called DRAM. We need to dynamically refresh the data. So this is because of the leakage of the capacitor. So let's look at what contributes to the leakage. So here we show the 1T1C configuration during the hold mode. This is hold mode. If we don't read or write the data, then the WL should be 0. You want to keep the data. This is the hold mode. So you want the data to maintain over time, but there are challenges due to the leakage. So here this is the stacked capacitor as we showed earlier. So you have the, of course I didn't draw U-shape, but this is a U-shaped capacitor. So then this is the storage node. And let's store 1 here. So that means this is VDD. Ideally, should be VDD. You have charge stored on this node. And then the word line is off during the hold mode. But the bit line here, as we discussed, we want to pre-charge to be half VDD. So you have half VDD on the bit line. And also here we draw this PN junction here because we want to emphasize this is a transistor, and transistor, this is NMOS. So you have N plus doping to the source and drain terminal, and then the substrate is P-type. So then from the PN junction point of view, so if you think about the PN junction, right? So we have N plus and P. So here's a PN junction. So here we draw this PN junction out. So here is a PN junction. That's this one. So here we have the leakage current to this storage node. Why? If you look at this transistor, it's in the subthreshold region. Because the gate is 0, but the source and the drain are non-zero. So this transistor is like this is 0, this is the VDD, and this is half VDD. So this is normally off because the VGS here is negative, but the VDS is non-zero. So still you have the leakage current from the drain to the source. If you recall the lecture 10 when we talk about the subthreshold current, right? So we have this. So this is the threshold voltage, but below that you have exponentially small current, but this is non-zero. So that is the leakage current. Sorry. this is IDVG. So here this leakage current basically is flowing, and this current is going to discharge this node. Although this is a small current, but over time it will leak. And also this PN junction, you see, the PN junction here, this is N, this is P, but N is VDD, P is ground. So this is reverse bias, PN, this is reverse bias. If you recall, in the lecture 7, we talk about the IV of the PN junction. So this is a reverse current due to the drift of the minority carrier. So you have the reverse current, and that means this is leaking as well. So you have those leakage currents to discharge this node. That means this voltage will decay over time. So if you think about the voltage over time, this is the VDD, this is the storage node voltage, and this is time. So it will decay over time. That's not good, because later you have the half VDD as your reference. If your voltage decay over time cross this half VDD, that means you are going to have error, because your 1 becomes 0. So before the decay to this half VDD level, we should refresh the data. So for example, when this decay happens to here, maybe, then we need to do the refresh at this moment to bring back the voltage to be VDD. So we have to bring this back, and then it will start decay again. But before it reaches this arrow state, then we have to do the refresh. And the typical refresh cycle by the industry standard today is about 64 milliseconds. So this is about 64 milliseconds before it become an error. So then you have to refresh every 64 milliseconds. And actually the refresh operation is naturally performed by read, not write. So here you have to be careful. This refresh is done by read, not by write, because of the write back feature built into the read operation, as we discussed earlier, right? So when you read out the data, even though it decays to here to start with, and then after the readout, then this will be naturally recovered to be VDD. So you can use the read operation to refresh the data. So any questions here? Okay, then let's look at the timing diagram for the refresh cycles. As we just mentioned, we need to do the refresh every 64 milliseconds. And let's assume the memory array. We can do this refresh row by row. So in the memory array, you have many word lengths, many rows. And then let's say this is word length 1, word length 2, and then the last is word length n. And here in this example, the number of rows is like 16 kilo. So that means every 64 milliseconds we need to locate to the word length 1 and then read the word length 1 to refresh the data in word length 1. So if you look at the timing diagram here, so this refresh cycle is this 64 milliseconds. And then if this is a t equals to 0, Then after 64 milliseconds, we have to go to the version 1. So here you start with version 1, and after 64 milliseconds, we need to go to version 1 to read the data from the version 1. So basically to refresh the data. And we can distribute the refresh across the rows. So basically, at first we refresh version 1, and then after some time interval, we move to version 2 and refresh version 2, and then after some time interval, we go to version 3, and then we keep moving that to the end of the array, and then we come back to the version 1 after 64 milliseconds. So the total refresh cycle is 64 milliseconds. And in this example, we have 16K rows. So the row to row interval will be this 64 milliseconds divided by 16K. That is 4 microseconds. So that is here. From version 1 to the version 2, this interval is 4 microseconds. So that means here we are looking at t equals to 4 microseconds. If you have version 3, then that will be t equals to 8 microseconds, and so on. And then till the end of the array, and then you go back to the first one. That is happen 64 milliseconds. So here you look at the one interval here from version 1 to version 2. So refresh basically is a one read operation. So if the read cycle time, that is the time for the read operation, if we assume it's 40 nanoseconds in this example. So here we're going to spend 40 nanoseconds to do this refresh. But between those refresh, you have the normal random access period. So here, between the version 1 and version 2 refresh, in this period or in this time frame, you can do whatever you like. You can read or write the data to arbitrary locations of the array, depending on your software program. You want to fetch the data from certain rows, then you can go to that row and then do the read or write of the data there. But at the time equals to 4 microseconds at this moment, you must go to version 2 and then read version 2 to refresh the version 2. Otherwise, the data in the version 2 may be lost. So this refresh to the version 1, version 2 is mandatory at that moment. That means you cannot do anything else. You have to go to that location and then read that location to refresh. But between that, you can do whatever you like, defined by the software program. So here we look at the percentage of the time that is used for the refresh. In this time interval, let's say 4 microseconds, you spend 40 nanoseconds to refresh one row. That means 1% of the time is for refresh. The rest, 99% of the time, is for your real operation. So this is how we look at the refresh. And this is a unique feature in the DRAM. And the refresh is not what we desire, but we have to do it. Otherwise, the data will be lost because of the leakage. So any questions? If no more question, I think that's all for today's lecture. And I think the key points are the 1T1C operation, like the recharge to half VDD to the bitline, and then you can calculate the delta V from the equation, and then understand the write back, and also understand the refresh operations. And the second meter grading is almost done, so we're going to discuss that on Thursday's class. We're going to go over the solutions, so please stay tuned for that. And if you know more questions today, then we're going to stop here. And thank you.